This is Unit 3, Lesson 1, Part 2, and our topic is the greatest integer function. Okay, so a couple quick fill in the blanks here just to give you an idea of what this function is all about. So the greatest integer function, first its notation is this. So we have f of x just like all functions, and then it's like this double bracket sort of thing. Like it kind of looks like it's just going to be a bracket and then there's an extra line in there. So whenever you see that, if you see it typed or written out, that stands for the greatest integer function. So this symbol right here, those double brackets, what that means is the greatest integer less than or equal to x. So basically what that means, this is what this third bullet point says, it means you always round down to the nearest integer. And so for that reason, we call it the floor function. Like whatever the decimal is, you just kind of chop it off and just round down to whatever the last integer was. So we're gonna practice that with a couple of these. So f of 7, if you were to take the greatest integer, so less than or equal to x, because it's less than or equal to 7, and 7 itself is an integer, this would actually just come out as 7. The next one, less than or equal to 2.3, the 0.3 is a decimal that needs to be chopped. So the greatest integer, because remember integers are whole numbers that can either be positive or negative. So the greatest integer that's less than or equal to 2.3 is 2. And then this, so the negatives get a little bit tricky because it seems like, oh, I'm just going to chop off the 0.8 and make it -4. But when you picture the way the negatives work, -4 is actually bigger than -4.8. And you need it to be the greatest integer less than or equal to -4.8. And that would actually be -5. So picture the integer that's to the left on the number line. That would give you a good indication of what you're supposed to be filling out. So now let's do this again. This one gets a little bit tricky because we're going to subtract 5 first, then find the greatest integer. So this, we're going to take 9 minus 5, which is 4. And then the greatest integer less than or equal to 4 just is 4 because 4 is an integer. So now we can do it again with this one. 0.5 minus 5. So when I subtract that, 0.5 minus 5 is -4.5. So just to give you a little reminder, we're looking for the greatest integer for -4.5. And so just like this one, if you just chop off the decimal, you get a -4, which is actually not what we're supposed to end up with. We want the one that's less than or equal to -4.5, and that would be -5. And then we can do this again with this one. -8.1 minus 5. When you subtract that, you get -13.1. And again, since it's a negative, you actually want the one that's to the left. So the greatest integer that's less than or equal to -13.1 would be -14. So that's just a little bit of practice with exactly what that definition means. We're going to spend the rest of our time looking at graphs so we can see what the pattern is and what these graphs are going to look like. So with this first one, we are going to plug in some different sample values. And so I want to make sure that we're plugging in decimals just so you can get a little bit of an idea of what this looks like. So we're going to plug in 0, but I also want to plug in like 0.5, and then we'll plug in 1. We'll plug in 1.5, we'll plug in 2, and then let's get an idea of what some negatives look like as well. So let's plug in -0.5, -1, -1.5, and -2. So I want you guys to get a good idea of what this, so this is just the simplest form. There's nothing else like added or subtracted or multiplied. So if we sub in 0, and now we're just basically doing what we're doing up here, we're just doing it in table form. So the greatest integer that's less than or equal to 0 is 0, because it already is an integer. So we could actually very quickly just fill in all of the integers on the table. Because like 1, if 1 already is an integer, and 1 is less than or equal to 1. So one of the tricks that you can remember with this function is if you plug in an integer, it's not going to change. Because part of the definition is that you want it to be the integer that's less than or equal to that number. And so 1 is less than or equal to 1. 2 is less than or equal to 2. Same thing with -1 and -2. So if you put an integer on your table, you don't even really need to think about it. You just know that it's going to come out the same. Now the decimals are the ones that you have to think about. So 0.5, the integer that's less than or equal to this number is 0. Because 0 is less than, but 1 is greater than, so you don't use 1. And then 1.5, less than or equal to that would be 1. And then negative 0.5, remember these ones are a little bit tricky, because this 0 is actually greater than this number. That means that negative 1 is less than that number. And this one, negative 1.5, the integer that's less than that is a negative 2. So we've got some patterns, we've got some points that we can plot. So let's go ahead and plot these points. So 0, 0 is right at the origin. 0.50 would be right here. It's like halfway in between those points. 1, 1 is right here. 1.51 is right here. 2, 2. And then negative 0.5 goes down to negative 1. Negative 1 is right on the corner there. Negative 1.5 goes down to negative 2. And negative 2 is right in the corner there. So you can see a little bit of the pattern of what it's going to look like. So if we look between 0 and 1, so here's a little trick, and this is the part that gets a little bit strange. Anything between 0 and 1 is going to land on 0. Because if I plug in like 0.9, it would get plotted at 0. It's like you'd see a point right there. If I plugged in 0.1, it would get plotted at 0. So you'd have a point right there. So you get just this like little snippet of a horizontal line. And that goes all the way up to 1, because when you actually get to 1, it jumps up. So what you end up doing is you have these little horizontal pieces where you have a closed dot right here, and you actually have an open circle on the end, and then just this little horizontal piece like that. Because when you actually get to the 1 isn't here anymore, it jumps up. And the same thing happens here. Everything between 1 and 2 ends up getting plotted at 1 until you actually get to the 2, then it jumps up. So you have this open circle here. So you get this perfectly repeating pattern. You also will hear this referred to as the stair stepper function, because it just looks like this little flight of stairs. So everything between 2 and 3 chops off at 2 until you actually get to the 3, then that jumps up. Everything between 3 and 4 goes to 3 until you actually get to the 4, and that pattern just repeats itself with every little horizontal line. And then we can work backwards here. Closed dot on the left, up to an open dot on the right, closed dot on the left, open dot on the right, and it just keeps going. And as always, we just plot until we run out of space. So it looks like that. So that is just like our original version of what this greatest integer function looks like. So our domain, you can plug in any number that you want into this domain. So remember this symbol that stands for all reals, it's kind of double block R. So just to remind you, if you're looking back and forget what that symbol is, I'll write it once here and then I'll just use the symbol for the rest of the notes. And then the range, so these are the Y values that come out. If you look at the Y values, they jump, like it hits -5, -4, -3, -2, -1, 0, 1, 2, 3, 4, but nothing in between. No decimals, no fractions get hit. So what we do is we say that the range, or the Y values, will only come out as integers. The Y values will never come out as decimals or fractions. You can kind of see that in this table right here on the right-hand column. So this, our symbol for integers, is this double block Z. So just to remind you what that means, because again, I'm going to use it on the rest of the notes, it means all integers. No decimals, no fractions, just integers. Okay, so that was our first one. Let's look at another one. So now this one is going to be similar to the one that we did for number 2, except you take the greatest integer and then you subtract 5. Okay, so like that part happens second. So we are going to do a little bit of a pattern here, see what we can fill in. So we're going to do 0. This is going to be our traditional table that we'll end up doing from now on, just to give you an idea. And then you just know that it does that same sort of like open circle, closed circle pattern. So this is what we're going to use anytime you guys make a table. So plug in a 0 first. Greatest integer of 0 is 0. And then you subtract 5, so we get -5. Greatest integer of 0.5 is 0. And then you subtract 5, so we get -5. Greatest integer of 1 is 1, minus 5 is -4. Greatest integer of 1.5 is 1, minus 5 is -4. Greatest integer of 2 is 2, minus 5. Greatest integer of 3 is 3, minus 5. And greatest integer of 4 is 4, minus 5. So notice we've got only integer values that are popping out of this function. So let's plot those points, see if we can figure out the rest of the pattern. So 0, negative 5 is right here. 0.5, negative 5 just moves over a little bit, and that's right here. 1, negative 4 moves up to that point right there. 1.5, negative 4 just moves over a little bit for its x value. 2, negative 3 is right here. 3, negative 2 is right here, and 4, negative 1 is right here. So you might be tempted to say like, oh, this just looks like a line, but now that we know what the general shape of the stair function is supposed to look like, this is enough to fill out what the pattern is supposed to be. So this one, we know this extends, and then once you hit the next integer value, there's an open circle. Then you jump up to the next one. It extends like this till we hit an open circle, and this pattern is perfectly repetitive. So even though we don't have quite as many decimal points on this graph, we should be able to figure out what this pattern is going to look like. So closed on the left, open on the right, and then you jump to the next value. And really, this is all that's going to show up on this graph. So this one, if you think back to some of your transformations, it looks like the stair-stepper function, and then the minus 5 makes it move down 5 units. So that's what's happening, is it looks just like the one on the previous page, but 0 moves down to negative 5, and so everything else was shifted accordingly. So domain. Domain is going to be all reals for every single one of these, because you can plug in any value of x that you want. And then the range for this one, you see that only the integer values are getting hit, so we use that symbol for all integers again. Okay, let's look at number 5. So this one, you subtract 1 before you take the greatest integer, and then you multiply it by 2. So let's use those same x values that I put up above. Like I said, this will turn into kind of our standard table, and we'll use that to figure out the rest of the pattern. So when I plug in 0, 0 minus 1 is negative 1. The greatest integer there is negative 1, and then you multiply by 2. So that comes out as negative 2. Do the same thing for 0.5. 0.5 minus 1 is negative 0.5, which jumps down to a negative 1, and then you multiply that by 2. Plug in 1. 1 minus 1 is 0. Greatest integer would be 0, and if you multiply that by 2, it's still 0. 1.5 minus 1 is 0.5, which drops down to 0. Multiply that by 2. 2 minus 1 is 1. That is already an integer, it's 1. And then you multiply it by 2. 3 minus 1 is 2, which again is already an integer. Multiply that by 2. And 4 minus 1 is 3, which is already an integer. Multiply that by 2. So those are our points that we can plot. So 0, negative 2 is right here. 0.5, negative 2 is right here. 1, 0 is right on the x-axis. 1.50, 2, 2, 3, 4, and 4, 6, which we're going to jump up right here. Okay, so our pattern looks basically the same. We go like this until we get to the next integer value. And then this one actually jumps up by 2, and the reason it's jumping up by 2 is because of this right here. It kind of scales it, stretches the whole graph out. So this goes like this to an open circle, here to an open circle, same thing here, and then this we can extend a little bit. So now we can also extend it back to the left. So we're going to jump down 2 units and then repeat that same pattern. So this domain and range is going to be a little bit different. The domain is still all reals. That's never going to change for the greatest integer function. This time the range, the only y values that are getting hit, you can see it on the graph, but you can really see it on the table. The only y values that are getting hit are the even values. So we are going to write even integers. Those are the only ones that get hit. And you could use that z if you wanted to. All right, so that is your greatest integer function.